All right, so last time we started out with looking at inflammation. It's a very important part of the process. So we watched these videos, right, which I have the links to in our Canvas site. We watched this animation, which I also have a link to. We talked about the different components, right? So we talked about why you see swelling, right? Why you see redness, why you feel heat or pain. And we started to talk about how this is initiated, this process. And it has to do with our cells being able to detect when they've been damaged, when invaders have gotten in. And the way they sense their world is they have receptors on the surface of their cells. Okay? And there's different types of receptors we'll talk about a little bit more, right? It's just introduced here. We're going to talk about more when we get to cell communication. So, an example are cytokines. Cytokines is a general name that we give to chemical signals that are used by our immune system specifically. So there's a chemical signal that your endocrine system uses. What's the general name we give to those chemical signals? Hormones. Hormones. So cytokines are like the hormones of your immune system, right? They are the chemical messages. They bind to receptors. They cause cells to do things. So an example of a very common type of cytokine that's very much involved in the process of inflammation that you've probably heard of is histamine, right? Because some people take antihistamines to stop inflammation related to allergy, right? To things that aren't actually going to harm us. Yes. It's okay. So inducers, right, things that would target inflammation and get it started is, as I said, microbes entering in or tissue damage to our actual cells. Blood vessels, when they're damaged, there's additional things that have to happen, right? There's a cascade of events that happen that coagulate that, because we don't want it just spilling out anywhere, right? Just like here, right? When good old Katrina happened and levees broke, that's not how we want things, right? We don't want the water going just about anywhere. Same thing in your body. You want to control blood flow, right? You want it to stay within the blood vessels, right? So when the blood vessels themselves are damaged, right, we need to repair that damage. We need to stop that flow of blood just willy-nilly into your tissues. And so you have the clotting cascade, right, which we're not going to go over in this course, right? But that's important for maintaining and damming up when you have damage to the blood vessels themselves. But we also have the increased permeability that's going to happen for intact blood vessels. Because remember, this is how the white blood cells get to the area when we have what we call inflammation. Now, does anybody know what over-the-counter drug you have in your medicine cabinet that actually impedes inflammation? Ibuprofen, also known as Motrin, right? That's a trademark name. The drug name is ibuprofen. You should only take ibuprofen when directed to do so by your doctor. Right? Because, what? What's Advil? No, Advil.
No, Advil is ibuprofen.
Yeah, Advil is ibuprofen. Aleve is naproxen. Tylenol is acetaminophen. Acetaminophen is different than ibuprofen. It deals with pain, right? Again, don't take it too often without consulting your doctor, right? Ibuprofen is one you really want to stay away from because it's an anti-inflammatory. So when is a doctor going to tell you to take that? When you've got prolonged inflammation, right? But when it's been going on for too long, right? Because inflammation is good in the beginning, but if it doesn't stop, it can create damage to your tissue as well, right? So it's one of these things, it's kind of like a sprinkler, right? When the sprinkler goes off, the sprinkler system in a computer lab, it's going to save the building from burning down, but what's the really bad news as far as that computer lab goes? All those computers are trash now, right? Electronics and water don't go so well together. Okay, so similar thing with inflammation, right? Is that you're going to have these cells coming into the area to destroy things, and that influx, right, and depending on what it has gotten in as well, if that goes on for too long and doesn't take care of itself, it itself, this influx of cells into that area, can be a problem. Right, so we have two different main types of inflammation. We have acute inflammation, right, which is short term. The macrophages, which is a group of the cells that go in and clean up the mess and eat the invaders, go in quickly, they clean up the mess, and inflammation stops. When acute fails, right, when they can't clean up the mess and they just keep coming, inflammation just keeps happening. This is referred to as chronic inflammation, and this can be bad. And this happens with some diseases because your immune system cannot eliminate the invaders. But they're going to keep coming because the invaders are there, right? And they're going to try and keep them in that particular area. So what will happen is especially macrophages will start fusing with each other and form these giant cells. And then with diseases like tuberculosis, T cells will even start infiltrating into the area, another type of white blood cell. That combination of the macrophages and the T cells form these masses we know as granulomas. And this happens in the lungs for tuberculosis because your immune system cannot kill this bacteria, and this bacteria can actually live inside your macrophages. So even though they keep coming, they're not killing it. And even with the T cell help, right, it's not enough to eliminate this invader. So the problem is these masses of white blood cells grow larger and larger inside your lungs over time, right? Without antibiotic treatment, you will eventually succumb to this infection. This infection in older times was sometimes referred to as consumption, right? And again, this is why it took a long time, right? There's some evidence that the famous gunslinger Doc Holliday probably died of tuberculosis, right, of consumption, that's what was wrong with him. So as we said before, right, the small blood vessels, and it's your venules, your capillaries in that area, they're going to dilate because we need lots of blood flow to that area. That blood is being called there so that those white blood cells, as we saw before, can attach, right, crawl out and get into that tissue and do their important job. Because you have increased blood flow, you see those signs of redness and heat. Because your blood is very hot, right? It absorbs most of the heat that your body generates. And it's how it eliminates it from your body as well. The fluids, because those blood vessels become leaky so that the white blood cells can get out, the major component, the fluid component of your blood, also leaks out into the tissues in that area. Right, so that's why you have the swelling, and then the swelling pushes up against the pain receptors there, right, and you feel pain a lot of times when you have inflammation. We're going to try and maintain, right, those clotting factors are in your blood, right, because we want to wall off, we want to try and keep stuff in that particular area, including blood vessels that are damaged, right? We want them walled off. We don't want the blood just spewing into that area. And depending on how much damage you have to blood vessels and to tissue, that's why healing can take a really long time sometimes, right? Because you have a lot of things that you need to heal, right? One of your classmates chopped her finger off. She's experiencing long-term healing right now. Chopped the tip of her finger off. The good news is it looks good, right? No infection. So, damaging effects of inflammation. So as I said before, right, it's like a sprinkler system, right? Once you turn this baby on, sometimes it's hard to turn it off, right? And it can be a problem in itself. Enzymes and toxic compounds from the cells, the phagocytic cells, the ones that eat the invaders, this can build up in that area and not be eliminated properly, and this can damage the tissues as well. So I also kind of equate to this where, you know, we'll bomb a building trying to get a terrorist, right? Anything in that building, though, also gets eliminated. Okay, so here, right, they go in and they just unleash everything, right, some of these cells in that area, and they're going to damage even some of your own good, healthy cells in that fight of trying to get the bad guy, right? So, unfortunately, it's not very targeted. So when inflammation happens in areas that are very sensitive, very delicate, so for instance in your lungs, right, where we really need to have as much surface area as possible for gas exchange, right? If we've got inflammation, influx of cells, and fluid getting in the way, then it makes it very difficult to breathe, right? If this happens to too much of an extent, right, we refer to pneumonia, right? Pneumonia is just an inflammation in your lungs. It could be caused by an invader, a bacteria, a virus, a fungus, right? It just really depends on what type of pneumonia you have that determines what's causing the problem. But pneumonia in general, that term just means inflammation in the lungs, right? And that can be very scary, very life-threatening if not treated properly and early. And if your immune system especially can't get a handle on it. So it can be severe and quite life-threatening. Other places where we really worry about inflammation are those membranes that surround your brain and spinal cord. So those are referred to as the meninges. Those membranes, when they become inflamed, you have what? Meningitis. So the itis, again, just refers to an inflammation of a particular area, in this case, the membranes. The problem with your brain and your spinal cord is they're very delicate systems, right? So delicate that what do we have encasing them to help protect them from injury? What's your brain encased in? Skull, bone, right? This is very hard. When you're an adult, right, it's not malleable. It does not, like your skin, when you have inflammation in the tissue associated with your skin, it can stretch, right? You can have that swelling, have some place to go. When you have swelling of those membranes around the brain, there's no place for it to go other than to push back on your brain. Same thing with your spinal cord, right? There is some flexibility in this space in between the vertebrae, the bone that surround your spinal cord to help protect it, right? But not a whole lot. So again, you get this squeezing effect. What can cause meningitis? An inflammation of these meninges, these membranes surrounding the brain and spinal cord. Bacteria can cause it, viruses, fungi, even some protozoa, right? So again, just because you have meningitis just means you have inflammation, right? And it's probably because you have some type of invader, right? They would have to investigate further by maybe taking some fluid, right, from the spinal fluid that surrounds the brain and the spinal cord, right, the CNS, to determine what may be the causative agent, so therefore how to direct treatment accordingly. Making a scary face, Devante. Yeah, they puncture between the vertebrae down in your lumbar region where the spinal cord itself tapers, so that hopefully when they puncture with the needle and take that fluid sample, they don't damage the spinal cord itself. So that's why it's called a lumbar puncture. That's why they do it down, right, in your lumbar region, the lower region of your spine. I've had it done. Yeah, it's not pleasant. It's not pleasant. But we have to try and figure out what's causing it, right? Because prolonged, your brain's going to shut down and you're going to die, right, if we can't figure out what's causing it. So cell death happens all the time in your body as well. Would you want inflammation to happen every time one of your cells dies? Right? Your red blood cells, right? Man, those guys are long-distance truckers. They're running through your body all the time at high speed. I mean, literally sitting at resting heart rate around 70 beats per minute, a red blood cell could lap your body in a matter of a minute, right? They're traveling that fast, right? So, you know, they're like long distance truckers. They get damaged very easily, right? They've got a really rough life. And so they have a very short lifespan. They only live about 120 days before they die, and, you know, we're continuously producing new ones to replace them. So one of the main areas where that happens, where we're removing those dead and damaged ones, is your spleen. If you don't have a spleen, it's the one organ you can live without, right? You don't have to have a spleen transplant. You'll never hear anybody having a spleen transplant, right? Your liver will take over taking care of those dead red blood cells. And recycling the hemoglobin anyways is a job of your liver. That one you cannot live without, right? There's no other organ other than the spleen that you can live without. So there's a process for death for your normal cells, right? If they haven't been infected, you know, their lifespan has just ended like a red blood cell, right? They're too beat up to do their job anymore. They need to be recycled. This process is referred to as apoptosis. It's programmed cell death, right? So the cell is damaged, it's not doing well, the body will initiate the death of that cell. In that process, inflammation is not initiated, right? We don't send out the triggers that we normally would for cell death, so we don't get that influx of more white blood cells than needed to the area. Cryopatesis, on the other hand, is when we do initiate inflammation, right? When cell death does trigger the cells to come to that area, right? So there's different ways the body can communicate, yeah, we need backup, we need inflammation, we need help, or no, we've got this one under control, right? This is a normal cell death that has to happen. Make sense? Okay. So when our cells die, when we have invaders, we need cells, and we have specialized cells that are going to come to that area, and they're going to gobble up the dead cell debris and the invaders. And they do this through a very intricate process that we know as phagocytosis. And so again, just like before, I've got some really cool videos of the real thing happening, right? So you can actually see, so we're going to go over to, there's the animation that goes into a little bit more detail, but I want to show you guys it really happening. So this is, I'll make it big.
Neutrophils are white blood cells that hunt and kill bacteria. In this spread, a neutrophil is seen in the midst of red blood cells. Staphylococcus aureus bacteria have been added. The small purple bacteria release a chemoattractant that is sensed by the neutrophil. The neutrophil becomes polarized and starts chasing the bacteria. The bacteria, bounced around by thermal energy, move in a random path, seeming to avoid their predator. Eventually, the neutrophil catches up with the bacteria and engulfs them by phagocytosis.
That's the one I want. And actually, I'll shrink it down. So they literally just took, and I might have sped up that video. I don't know if that was real time. I'm feeling it was a little bit faster. So our white blood cells can move just like amoeba. That little black mass at the back, I have no idea. I've had a student ask me before about that. I'm like, I don't know. But the red blood cells, right? So they literally just took somebody's blood, put on a microscope slide, added some bacteria to it, and filmed it. Those bacteria, although they don't do this on purpose, just like us, we give off a particular odor, right? Bacteria release waste products and such. They have a, you could say, quote-unquote, odor. Those are the chemoattractants, right? The chemicals that they release, our neutrophils specifically really know what bacteria smell like in general, right? And they're going to chase them down. That particular bacteria is not motile, but remember, your blood is liquid, right? So they're bounced around by the thermal energy, right, that's going on there. But the one that's actually really moving is that neutrophil, and he's engulfing it. And the next one that I have for you guys is where they've actually taken out just the neutrophils. So these are
These human neutrophils, taken from the blood,
are specially designed for this hunting and devouring ability. So they're a special type of white blood cell. So we'll make it big first. Then we're going to...
The graduate student are mobile cells that will quickly migrate to sites of injury to help fight infection. They are attracted there by chemical signals that are released by other cells of the immune system or by invading microbes. In this experiment, tiny amounts of chemoattractant are released from a micropipette. When neutrophils sense these compounds, they polarize and move towards the source.
So it definitely looks like an amoeba here, huh?
When the source of the chemoattractant is moved, the neutrophil immediately sends out a new protrusion, and its cell body reorients towards the new location.
So in that case, you know, they purified the chemicals that they know that they will be attracted to, and purposely just put the neutrophils there. And you can really see how they head right towards that attracted, right? Right towards what it is that they are needing to attack. So this process, and you got to go to presentation mode to be able to play the one that's embedded in my PowerPoint. So definitely receptors are involved, right? So I definitely want you guys to pay attention to that as you watch this animation, right? Because we're going to go into a little bit more detail of this process with this animation.
In phagocytosis, phagocytes are attracted to the area of invasion by chemical products of the microorganism, phospholipids released by injured mammalian cells, or by components of the complement system. The phagocyte moves into the area of invasion and then attaches to the microorganism. The attachment is mediated by a variety of surface receptors, including antibody, lipopolysaccharide, and complement receptors. For example, the C3b component of complement coats bacteria or other particles and then binds to C3b receptors on the phagocyte. This process of coating to enhance phagocytosis is called opsonization. The microorganism is then engulfed by the phagocyte into a vacuole known as a phagosome. Vesicles in the cytoplasm called lysosomes fuse with the phagosome, releasing digestive enzymes such as lysozyme and proteases into the phagosome. The structure resulting from this fusion is called a phagolysosome. Inside the phagolysosome, microorganisms are killed and digested. Finally, the digested contents of the phagolysosome are eliminated from the phagocyte by exocytosis.
So they can't really show you that in the videos, right? But we definitely see them going after them and grabbing them, right? And as they said, why do they do this is they're attracted to that area. So this is a chemoattractant, right? Chemotaxis meaning chemical, right? Taxis movement in response to a chemical. So this is a chemical that's released actually by our body, C5a, that we're going to talk about when we get to cell communication in the complement system. The C here stands for complement. Another thing from that same system, hence the C, is a molecule that our body produces that actually binds to the surface of bacteria. But in addition, notice they mentioned in the video lipopolysaccharide. Do you guys remember what bacteria have that on their outer surface? Gram-positive or gram-negative? Gram-negative, because they have that outer membrane. I wasn't kidding, y'all, when I said I wasn't going to shut up about gram-positive and gram-negative, right? All semester long, you will hear those two words. Okay, so these cells, these specialized cells, these phagocytic cells, have receptors for things like lipopolysaccharide or components that we produce like this C3b. Another component that's very common to our immune system are antibodies, right? So these are proteins that we produce as well that will attach to the surface of the bacteria. But, you know, we have lots of receptors on our cells that can recognize general patterns, like the lipopolysaccharide, like the peptidoglycan, that substance that makes up the cell wall of bacteria, right? And would probably be the outermost covering for something like a gram-positive, right? The flagellin protein that makes up their flagella, we have receptors for, right? So we've got to first be called to the area, right? Those cells are going to be called to that area, usually in the essence of inflammation, right? That's the first thing. Inflammation is setting off that signal, that chemical signal, sending out saying, help, help, right? And then the helpers are these phagocytic cells because they have the ability to eat and gobble up these bacteria, the viruses, even parts of our dead cells that have been damaged. The next step is actually physically grabbing onto, attaching, recognizing, right? So these receptors that grab on actually only bind to certain things. So in this example, they're the receptors for C3b. So they're grabbing on to C3b, that this cell has been coated in. That coating process, they called it opsonization, right? We're gonna see that again later. So that's a very specialized process where special molecules, C3b or antibodies, are specifically binding to that substance and helps facilitate this attachment, this recognition, this very first crucial first step. And then they can begin engulfing it, right? So the cell, once it attaches, it recognizes it, it's going to push its membrane around, right, and begin engulfing whatever it is they're attached to, a virus, a bacteria, parts of dead cells. And they'll surround them in such a way that they create a vesicle. This is a very specialized endocytosis, where we've definitely engulfed something we want destroyed. So this is called a Faygo Zone. And again, we've encased it in the membrane within the cell. We don't want them running free inside of our cell, right? This is a bad guy. This is a bacteria. Then we're going to fuse the lysosomes with it. Lysosomes, remember, are vesicles, membrane-bound, that contain digestive enzymes. So they'll fuse with the phagosome, and we just fuse the name too, right? It's called a phagolysosome now. And we're dumping those digestive enzymes onto this bacteria. Then we're going to digest it, right, with those digestive enzymes, and then they're going to spit it out, basically, by exocytosis. Some cells are going to go one step further. They're actually going to keep pieces of this and present it on their surface. This is called antigen presentation. Did you guys see that in the web pages that you looked at? Right? So where they kept a piece, right? But in order to get a piece, they had to first phagocytose it, right? Digest it. So we've got this wonderful system, right, that you've read a little bit about, hopefully before you came to class today. Those nice summary web pages with the cute little drawings, right? I love the little drawings of the cells and the analogies they make. I lost my train of thought, clearly. Pause. Right. What did I want to say? I don't know. It'll come to me in a second. So there are several different types of white blood cells that can do this process. The two main ones that we talk about are macrophages and neutrophils. Oh, I remembered. I'll go back to it while I still remember. Same thing though, right? So remember I said earlier that macrophages can't kill Mycobacteria tuberculosis? Okay. So Mycobacteria tuberculosis is still engulfed by this process, right? And the problem with that particular one is that when the lysosomes fuse with the Faygo zone, those digestive enzymes aren't powerful enough to kill the mycobacterium. So the mycobacterium actually can grow within that phagolysosome. So again, even though we have these protection, we still get sick, right? The reason why we still get sick is just like how someone could still break into my house. Even though I got an alarm system, right? A neighbor who's semi-retired so never goes anywhere. I used to have a really good guard dog. Someone could probably still get into my house if they really wanted to, right? Because they could disable the alarm system. They could disable the dog. They could pick the one time my neighbor goes out to the grocery store, like once a month, right? And get in and take what they want. Which I got news for you, there isn't anything really to take. Right? But they could do it. Just like pathogens could get past these defense mechanisms. Some of them can avoid the process of phagocytosis altogether, right? Some of them can stop being tagged by opsonization. They can actually stop our antibodies or stop our proteins from binding to their surface. If we can't see them, can we attach to them? No, right? And that's the first step. We've got to be able to attach. We've got to be able to recognize. So if we can't attach to them, we can't recognize them, our phagocytic cells aren't doing us any good, are they? So that's one way that some invaders evade our immune system, right? Can stay within our bodies and grow and not be eliminated. Others can get into the Faygo zone. So Shigella can actually get itself out of our phagosomes. Right? It can escape from this membrane. So since it escapes, the next part, when the lysosome fuses, it's not even there to be killed. Right? He done jumped out. Mycobacterium, as I said, and other ones can survive the enzymes that we have. We don't even destroy them. So although we have these protection, right, there are microorganisms out there that still make us sick because they get past these levels of protection. Right? That's why they're quote-unquote pathogenic, right? They cause disease because they can get past or at least evade our immune system long enough to make us sick. So how do our two main phagocytes work? Because why do we have two, right? Well, because each one of them kind of does things a little bit differently. Macrophages are found always in our tissues. They're called monocytes in your blood, and they differentiate into this cell type we know as macrophages. All your tissues have resident macrophages. So you have guard dogs on guard all the time, ready to gobble up any bad guys that hop the fence. Right? They survive after phagocytosis, right? So they can engulf, they can kill, they can engulf and kill a lot of stuff, and they're still going to survive this process. They can be activated by T cells to increase their killing power. That's why in granulomas you have T cells as well, right? So you've got giant cells where the macrophages, when they can't kill it, they're going to keep surrounding it. And then T cells will come in and they're going to try and help, right? They're going to be like, well, that set of enzymes didn't work, right? Those bombs didn't work. Let's try these other bombs, right? Let's make these other enzymes, these other destructive things. Let's see if they'll kill it. The bad news is when it comes to tuberculosis, even with that help, even using all the bombs, all the arsenal that we have, we can't kill those guys. Right? Your immune system cannot kill them. Right? So the macrophages keep coming, the T cells keep coming, these masses form, these granulomas form in the lungs, and we're not able to eliminate the invader. This is also another reason why people who have tuberculosis, when they take medication, it's not like when we have a normal bacterial infection, right? You can take it for about a week and it's taken care of. This is why they have to take antibiotics sometimes for months, because you've got to try and get to the ones that are inside those cells. You've got to be able to eliminate them. So specialized drugs for that. The other bad news is, do all the drugs we have work against all the different types of mycobacteria? No, we have different strains of Mycobacteria tuberculosis now. We have strains that are called multi-drug resistant, which means that it's resistant to quite a few drugs, right? So we only can use specific ones. And then we've got strains that are now known nowadays as extremely drug resistant. What does that mean? We're very limited in the amount of drugs that we have available that are effective against that strain of bacteria. And that's what's really scary about that. That in as little as 10 bacteria, right? Because, again, our immune system can't kill them. You can get this disease. So tuberculosis is no laughing matter. So those are our macrophages. Macro meaning big. They're our big eaters. Neutrophils, on the other hand, fall under a group known as granulocytes. These guys have specialized granules in them. So like lysosomes, they contain digestive enzymes and other substances. These guys, neutrophils, you'll only find them in your tissues during inflammation. They're only called out of the bloodstream into your tissue when we're experiencing inflammation, when they're being called there. And the reason for this is these guys are super killers. They'll sometimes degranulate. They're going to release their granules, right? So they're not even going to just engulf and phagocytose and kill. They'll release their toxic compounds into your tissue, right? And so this is like the sprinkler system part, right? It just releases its bombs. It's going to kill anything in its path, including itself, right? Neutrophils die when they degranulate. And these are very short-lived cells. Right? Even when they're going through phagocytosis and stuff like that, they don't really hang around. They get very damaged by this process of eating and eating and eating these bacteria or viruses or dead cell debris. The pus component, right, when you have an infected wound and it's very pussy, that's the neutrophils, right? That's mostly influx of lots and lots of neutrophils and dying neutrophils at that. So you've got dead cells, you've got dead tissues. And why you really want to avoid pus is that clearly you've got some type of infection, right? Bacteria usually are the ones that are going to really elicit this really strong response and get a lot of cell death and neutrophil death in the process. So you also have the pathogen present in that pus. And that's why, other than it being kind of gross, you want to definitely avoid contact with it. These guys, as I said, have the greatest killing power. My nickname for these guys is suicide bombers, right? Because they will literally kill themselves in the process of trying to kill the bad guys. Also, recently we found, our eukaryotic cells have a very complex cytoskeleton, right? They have microfilaments and microtubules and intermediate filaments. They can literally shoot their cytoskeleton out of their cells. Right? So again, they're dying in this process, but they can do it in such a way that they create like a net. And so that they can try and trap the invaders in that area, right? We want to try and contain the area. So when you get an abscess that forms, right, that's when they're walling off the area because they're not able to eliminate it, right? And why pus comes out of it. You get all those dead neutrophils and dead cells. And it's also why it can be infectious, right? It can be a source of infection because it is a site where we're not eliminating the invader, right? Your immune system is doing the best it can, but it's not being successful. And these guys are the most abundant in your blood. Right? So that whenever we need them, they're there. We don't have to wait for them to be made in your bone marrow. they're there. So next time we're going to really focus in on the different types, all these different types that we've started to mention, right? Especially the main granulocytes and these mononuclear phagocytes and their other functionalities, right? The objective, we really are going to focus in on what do these guys do, right? What's their function? So, and then that information is in the next PowerPoint, which is cell communication. Remember, under assignments, if you haven't done it yet, it's going to mark it as late, but that's okay. All right, I really wanted you guys to read those immunology web pages before class. All right, those two that I referred to today. If you haven't, still read them. I read it every time I teach this course, y'all. Every time I reread these pages. They're that good. Okay? There's a game you can play if you want. But notice that when you guys click on this assignment, down here there's an area where you can enter your 2 comments and then hit submit. No, here, I'll show you.
Yeah, I noticed I sent you an email because I didn't understand it.
Yeah.
That was because I was using my mobile device, and when you use the app, it doesn't show everything. And I went on my computer and then I saw everything. I had to actually submit.
Yes. Yeah, I saw, like, the other day when I looked at it, it looked different than I looked at it today. But hopefully, somewhere, depending on which device, right, which browser apparently you might be using, when you actually click on the assignment, let me find it, there should either be, like it, see this, on my other computer, there was a text box that opened up. Here, it's saying submit assignment. Somewhere on this page, the assignment page, there should be some place where you can type and submit.
So you hit the button?
Yeah, hit the button and then see it pops up. For some of you, this might automatically pop up and you can type and then you can hit submit, right? So make sure you do that so you get your points, right? Everybody wants their points. Get it done as soon as possible.
I think it came up as a reply on your own.
Oh, you replied to my announcement and I turned that off. So just go in and you can copy and paste that into here if you want, or just redo it.
Okay, I'm here.
Okay, yeah.